In 1982, the engineers behind Venera 13 believed they had already solved the hardest problems. They had solved pressure. They had solved heat, temporarily. They had solved impact survival. Venus was no longer unknowable. It was measurable. But there was one assumption no one questioned. Light behaves normally. That assumption was built directly into the camera system, and it was quietly dismantled by a painted strip of metal no larger than a cigarette lighter. By the early 1980s, the Soviet space program had spent over a decade learning how Venus destroys machines. Early probes were crushed before reaching the ground. Later probes survived for minutes, then tens of minutes. The engineers adapted. They replaced aluminum with forged titanium spheres. They pre-cooled internal compartments below freezing. They filled the lander with phase change materials to absorb heat during descent. By the time Venera 13 launched, survival was no longer theoretical. It was engineered. The next objective was precision. Previous landers had transmitted black and white panoramas. Those images proved the surface existed. They revealed rocks, slopes, fractured plains. But grayscale hides chemistry. Color reveals oxidation states. Color reveals mineral composition. Color reveals surface processes. If Venus had undergone different geological evolution than Earth, color could expose it. So the engineers upgraded the imaging system. The camera was not a camera. Venera 13 did not carry a conventional photographic camera. Glass lenses would have been structural liabilities under 90 atmospheres of pressure. Electronic imaging sensors would have failed under sustained heat exposure. Instead, the lander carried a telephotometer. The device remained inside the pressure vessel. It looked outward through a thick quartz window only a few centimeters wide, small enough to survive the pressure differential. Behind the window, a mirror rotated mechanically. The system scanned one narrow vertical slice of the landscape at a time. It measured brightness through different color filters. Red pass, green pass, blue pass. The probe did not transmit images. It transmitted numbers. On Earth, computers reconstructed those numbers line by line into panoramas. The process was slow. A full-color panorama required tens of minutes. If the lander overheated mid-scan, the image would cut off permanently. The engineers were trading speed for durability. But durability required something else: calibration. Within the camera's field of view, the engineers installed a simple painted panel. 4 strips: white, red, green, blue. This was not decoration. It was an anchor. The assumption was straightforward. Even if Venus tinted the scene slightly, sunlight reaching the surface would still contain a broad spectrum. The panel would reveal how much distortion occurred. Scientists could then mathematically reverse the shift. The calibration strip was a safeguard against atmospheric uncertainty. It assumed that full-spectrum light still existed at the surface. That assumption was wrong. What the panel showed. When the data arrived, the landscape appeared drenched in orange. This was expected. Venus is wrapped in dense carbon dioxide and sulfuric acid clouds. The atmosphere scatters and filters incoming sunlight. But the calibration strip revealed something more severe. The white panel did not appear slightly warm. It appeared orange. The blue strip was not tinted. It was nearly black. Green collapsed into brown. Red changed very little. This was not camera bias. It was not transmission error. It was not post-processing. It was atmospheric physics. Blue wavelengths were not merely reduced, They were almost entirely absent by the time sunlight reached the ground. The surface of Venus is illuminated by spectrally incomplete light. Why this was not a minor detail. On Earth, true color imaging assumes a balanced solar spectrum filtered moderately by our atmosphere. Venus does not provide balance. Shorter wavelengths are absorbed and scattered out before reaching the surface. What remains is dominated by longer wavelengths, red and orange. This has a crucial consequence. You cannot reconstruct information that was never recorded. The telephotometer captured reflectivity under red-dominant illumination. If a rock reflected blue strongly, the system would not register it, because blue photons were not present to reflect. The calibration strip proved that part of the visible spectrum never made it to the surface. The image data was not distorted. It was incomplete. The geological implication. Most viewers interpret the Venera panoramas as chemically definitive. The rocks look oxidized. The soil looks basaltic. The terrain appears uniform. But these interpretations rely on reconstructed color models. Scientists applied corrections based on laboratory simulations of Venusian atmospheric filtering. Those corrections are mathematically sound, but still model-dependent. The calibration panel did not give a direct neutral reference. It showed that neutral illumination did not exist. This means every true color Venus surface image is a calculated estimate, not a direct observation under white light. The biological constraint. Most discussions of life on Venus focus exclusively on chemistry. Surface temperature, roughly 475 degrees Celsius. Pressure, approximately 90 atmospheres. Atmosphere, carbon dioxide with sulfuric acid aerosols. Under these conditions, water-based biochemistry appears impossible. But the calibration strip introduced a second, rarely discussed constraint: optical environment. On Earth, biology evolved under full-spectrum sunlight. Photosynthetic pigments absorb specific wavelengths. Visual systems evolved to detect spectral contrast. Camouflage exploits color differentials. Venus removes much of that spectrum. If surface-adapted chemistry existed, even exotic chemistry, it would evolve under red-dominant illumination. Its pigments, if any, would not resemble terrestrial chlorophyll. Its reflectivity profile would not match Earth-based biological expectations. Under compressed spectral lighting, color differentiation collapses. Contrast weakens. Boundaries blur. The perception system was never designed for that. The Venera telephotometer was optimized for survivability. It prioritized mechanical robustness over spatial resolution. It scanned line by line. A single panorama required continuous operation over extended time. Under diffuse orange light, shadows were soft. The thick atmosphere scattered illumination evenly, eliminating sharp contrast. If something shifted slowly across the surface during scanning, the result would not be a clear moving form. It would manifest as subtle tonal variation, possibly dismissed as noise. The system was not built to detect biological motion. It was built to survive long enough to prove the surface existed. The quiet limitation. The calibration strip proved something fundamental. The search for life on Venus has always been constrained by more than temperature. It has been constrained by perception. Our remote sensing techniques assume spectral diversity. Our biological detection strategies assume pigment contrast. Our imaging interpretation assumes white reference. Venus provides none of these. Even if the probability of surface life is extremely low, the detection challenge would be compounded by optical compression. A structured object could appear geological. A subtle pattern could appear random. A reflectivity anomaly could be invisible, not because it is hidden, but because the light itself is incomplete. The engineering irony. The engineers installed the calibration strip to eliminate uncertainty. Instead, it revealed a deeper layer of it. They had conquered pressure with titanium. They had delayed heat with phase change chemistry. They had survived impact through structural reinforcement. But they could not change the spectrum of sunlight. The lander operated for 127 minutes. Its internal temperature gradually rose. Lithium nitrate inside the pressure vessel melted, absorbing heat. Eventually, the thermal buffer was exhausted. Electronics failed. Transmissions ceased. The titanium sphere became another object resting on the Venusian plain. But before it died, it transmitted a quiet anomaly. White does not exist there. Blue barely reaches the ground. The surface is illuminated by partial sunlight. The uncomfortable question. If we ever send another lander and survive again, what would we actually see? Would we deploy cameras calibrated for incomplete spectra? Would we adjust detection algorithms for red-dominant illumination? Would we search for life using Earth-based optical assumptions? Or would we acknowledge that our perception tools are planet-specific? The Venera 13 panorama remains the only true ground-level color image from Venus. Every modern rendering traces back to those scan lines. And in the lower portion of that frame sits a small painted strip that proved something unsettling. Even our most direct observations are constrained by environmental filtering we cannot bypass. Venus may be sterile. Its surface may be chemically hostile beyond any biological tolerance. But the calibration panel demonstrated a deeper truth. The challenge of Venus is not only survival, it is interpretation. We have touched the surface. We have measured its temperature. We have recorded its sound. But we have never seen it under neutral light. Until that changes, every image remains a reconstruction, and every search for geology or life operates within a spectrum that is physically missing pieces. That limitation was not discovered by theory. It was discovered by a 6-centimeter strip of paint in the corner of the only real photographs we have. And almost no one noticed it.